All right, early evening, everyone. We're almost done. Just bear with us for 2 more talks. My name is Shaina Wilburn, and I am a professional meteorology major at Mississippi State University. And today I'll be talking to you about the effects of the 2013-2015 warm water anomaly, also known as the Blob, on the productivity of the Santa Barbara Channel. So throughout this presentation, I'll give you a little bit of background about the Blob, how did it form, explain why we care about this topic, and then explain my methods, conclusions, and results that I got from this project. So let's start out by talking about the Santa Barbara Channel, what makes it so special. Well, the Santa Barbara Channel is located on a blip in California's coastline, which makes a really interesting area to look at the wind fields and how they affect other processes in that area. There's also a really large variety of phytoplankton in the channel, which makes it a good place to look at chlorophyll-a values, which we can use to estimate the amount of phytoplankton and then estimate the productivity of this area. And so productivity is variable by season to season, but it can be affected by any oceanic and atmospheric anomalies that occur, such as the ridiculously resilient ridge. This ridge, lovingly and scientifically referred to as R-cubed, was an area of persistent atmospheric high pressure that basically reversed meteorological norms during the winter of 2013. So typically in the Gulf of Alaska, we have a low pressure area that forms called the Aleutian Low, and this area of low pressure is basically responsible for bringing in moisture to the west coast, and it cools things off and makes everyone happy on the west coast because it's not so dry anymore. However, in the winter of 2013, an atmospheric ridge formed and parked itself right over the Gulf of Alaska and prevented the Aleutian Low from forming. And this high pressure resulted in 12 millibar deviations from standard sea level pressure. And 12 millibars doesn't sound like that big of a deal. We can see that in normal day-to-day weather patterns. However, when we're talking on the scale of climatology, 12 millibars has the ability to change the things that are happening in that area and cause other events that we haven't seen before. And so one of these events is the Blob. So we all know and love the Blob, but I want to draw your attention right to that little black box. So the Blob formed in late 2013 up in the Gulf of Alaska and eventually reached all the way down into Baja California before finally dissipating by the end of 2016. And in this area, that's where Santa Barbara is. And in this graphic from NOAA, you can see that in some areas, you see sea surface temperatures as high as 4 degrees Celsius above the norm. And this is extremely important when we're thinking about the things that are happening under the ocean surface and atmospherically, especially productivity. So a lot of us have mentioned productivity, but what exactly is it? So productivity is basically the amount of photosynthesis that is occurring in an area. The more phytoplankton you have, the more photosynthesis is occurring, the higher productivity values you have. And so there are 2 main factors that go into productivity, and the first is sunlight. So the sun's rays reach the top layers of the ocean, and the phytoplankton there can readily use that energy and photosynthesize. They're warm and they're happy. The second factor is upwelling, and upwelling is a process in which winds flowing parallel to the coastline push the warmer sea surface levels away from the coast, making room for colder, more nutrient-rich water to reach the surface. And the phytoplankton can then use all of these nutrients, similar to kelp, like Avery and Sarita mentioned, and they're happy, they can reproduce and photosynthesize, and we get higher productivity values. So why do we even really care about something called the Blob? Or why is phytoplankton important? Well, the Blob is important to think about because as global temperatures continue to warm and sea surface temperatures continue to fluctuate, we could possibly see more events that are as anomalous or more anomalous as the Blob. Phytoplankton, as we've heard multiple times, are the bottom of the food chain, and so if something happens to them, something happens to all of the higher trophic levels, and it could cause a potentially disastrous imbalance in the ocean, and we don't really know what that would look like. So in learning all of this, I was thinking, okay, so the Blob affected sea surface temperatures, that's why it was such a big deal, but why else do we care, and what else did it affect? So I calculated anomalies for each of these parameters, and then compare them to past years since 2002, the beginning of MODIS, and I used them to look and see how significant the Blob's anomalies actually were. And we can use chlorophyll-a values from MODIS because chlorophyll-a, like I mentioned earlier, is a good indication of how much productivity because it can show how much phytoplankton is in an area. Then I wanted to calculate wind curl and upwelling indices from UNV wind components to see if there was a relationship between upwelling and sea surface temperature or chlorophyll to get a better idea of what was going on. I started off by looking at variables that seemed like they should be directly related, so chlorophyll and sea surface temperature, and then upwelling and wind curl. And if you look at chlorophyll and sea surface temperature, there is a negative relationship between the two. As sea surface temperature increases, chlorophyll tends to decrease. That kind of makes sense. Similarly, with upwelling and wind curl, as wind curl increases, upwelling increases. You might notice, however, that the R² values are super low, suggesting that there isn't actually as strong a relationship as I'm making it sound. And that is just because there are so many variables that go into these values that you're seeing on these plots. For example, chlorophyll-a and sea surface temperature, the majority of phytoplankton like cold water. However, there is a small handful of phytoplankton that messes up the relationship because they actually flourish in warm water. Similarly with upwelling, they are both related to each other, but not as a direct result of each other. And so they can both increase if wind speed increases, but if wind curl increases, that doesn't necessarily mean upwelling will increase. Next, I looked at upwelling versus sea surface temperature and chlorophyll. And so with chlorophyll, there is another trend that you can see. Whereas upwelling increases, chlorophyll increases, and that makes sense. Upwelling brings nutrients to the surface. But there's still a low R² value. And it's a similar situation to the previous plots because, like sea surface temperature, there is a small group of phytoplankton that don't actually do well during an upwelling event. They bloom on the heel of upwelling events. So it makes them look like they're not as related as they actually are. Now, sea surface temperature and upwelling is a little different. They're related to each other. However, they both have other things affecting them, like seasonality. So if you look at this graphic on your right, it is a climatology, or a graph of climatology of sea surface temperature and upwelling index from 2002 to 2017 mapped against the relative solar heat flux of a year. So I want to draw your attention to May specifically. If you look at sea surface temperatures, you can see they begin to increase in May, which follows the relative solar heat flux. It starts getting to its peak there. However, upwelling indices already begin to decrease. And so while sea surface temperature is increasing, upwelling is already starting to decrease. And that kind of sort of makes sense. But then if you look at when upwelling is increasing, sea surface temperature doesn't really change. And so it's just an example of how a lot of these relationships have more than one thing happening. And so you can't really get a perfect relationship between the two of them. So after looking at the climatological relationships between these things, I removed the climatology and just wanted to look at the anomalies. So starting with sea surface temperature, you can see that there are both positive and negative anomalies that have occurred since 2002, but the blob highlighted in this little box was so anomalous that it actually raised the zero axis slightly higher, so some years look colder than they actually were. With chlorophyll, again, there are both positive and negative anomalies, but during the blob, it was pretty much below average. So we can assume already that productivity dropped during the blob. And just an easier way to see how sea surface temperature and chlorophyll did initially affect each other is just to put them right on top of each other. And so right here, during the blob, as sea surface temperatures increase, chlorophyll immediately decreases, and even when there's a little blip, chlorophyll immediately reacts. So the next two anomalies were wind curl and upwelling, and these are a little bit more difficult to analyze because they can change from so many factors. They can change just with wind speed or wind direction, and then seasons play into these values as well. So with wind curl, it kind of looks like during the blob that it got a little bit more negative, but a similar thing happened in 2012, so we can't actually say that the blob caused these things. With upwelling, it's a similar story. It looks like it got more negative, even turned into downwelling at points, but something happened before, so we don't actually know if the blob affected these things directly. Another way to look at upwelling to get a better idea of how these things actually reacted to these warm water anomalies is to look at cumulative upwelling. And cumulative upwelling is basically when you take an upwelling index January 1st of a year and you just add the subsequent days. And you can get a graph that looks like this where it shows you where upwelling starts and then how strong it was during that year. So the lines in gray are the climatology years, 2002 to 2017. And with the black being the mean average cumulative upwelling indices. And the years of the blob, which we care about, are 2014, 2015, and 2016, which you can see in these yellow lines. And they are below average. However, again, you still can't say that the blob is the reason why they were below average because it wasn't a singular event. There are still other years that are below average. And so in conclusion, we can see that there were high sea surface temperatures. Obviously, that's why the blob was such a big deal. Upwelling was lower than average, even if that wasn't directly because of the blob. But because there was lower upwelling and because there were higher sea surface temperatures, productivity did drop during the blob. Curl was not directly affected. However, this could also be due to the fact that my data was very poor spatial resolution. It took a very large area of values and then averaged them all into one place. So you can't see the local changes in wind values just from little things. We can also conclude that there are complex relationships between all of these parameters, and it's really hard to say for sure what affected one thing or if one thing changed something significantly because there's so many other things happening here. So some future work would be to find wind data with better resolution so you can actually use it and see what's going on. Another step would be to remove climatology from scatter plots to see a better depiction of the relationships and see if anomalies are more related than just overall. And then another thing to look at would be just more anomalies. Look at strong El Nino events or La Nina events to see if we could see similar results as we did with the blob with other events. And I would also love to look at how the blob actually affected the meteorology versus just the oceanic processes. So I would like to take a moment to acknowledge Henry. Thanks for all your patience and help. Rafe, thank you for your support. Emily, thank you for putting everything on, and then everyone else. It's been super fun to form this little family. Thank you for Megan for taking such good pictures that I used in my final presentation. And with that, I will take any questions.